You've been lied to about the origin of the universe. For nearly a century, scientists have told you that the Big Bang is a fact. They have told you that space itself is expanding. They have told you they understand how it all began. But here is what they are not telling you. The most powerful telescope ever built is showing us an early universe that looks nothing like what the Big Bang predicts. Dark matter remains undetected after 50 years of searching. The universe is expanding at two completely different speeds at the same time, and a growing number of physicists are starting to whisper what was once unthinkable. What if the Big Bang never happened? If you want to know the truth about cosmology that mainstream science does not want you to see, you need to be subscribed. Let me show you the 33 lies. There is a telescope floating in space right now that has just shattered everything we thought we knew about the beginning of the universe. When astronomers first analysed the images from the James Webb Space Telescope, they did not celebrate. They panicked. The galaxies they were seeing should not exist. They were too big, too bright, too mature. According to the Big Bang theory, these galaxies are older than the universe itself. Welcome to the crisis in cosmology. For nearly a century, you have been told that the universe began with a massive explosion 13.8 billion years ago. You have been told that space itself is expanding. You have been told that scientists understand how it all started, how matter formed, how galaxies grew. But here is what they are not telling you. The most powerful telescope ever built is showing us an early universe that looks nothing like what the Big Bang predicts. Measurements of how fast the universe is expanding give us two completely different numbers that cannot both be true. The lithium that should exist after the Big Bang is mysteriously missing, and a growing number of physicists are starting to whisper what was once unthinkable. What if the Big Bang never happened? This is not fringe science. This is mainstream cosmology in full-blown panic mode. In 2025, a team led by Duke University published results so shocking that they declared the Hubble tension is no longer just a problem. It is now a crisis. That same year, studies showed that ancient galaxies appear exactly when and where they should not. The predictions are failing, the models are breaking, and the explanations are getting more desperate. Over the next hour, I am going to walk you through 33 specific claims about the Big Bang that turn out to be wrong, misleading, or based on assumptions that are now crumbling. Some of these are outright lies, others are half-truths that scientists cling to, because admitting they are wrong would mean rewriting 100 years of cosmology. We're going to examine what the James Webb Space Telescope is actually showing us. We're going to break down why the universe seems to be expanding at two different speeds at the same time. We're going to look at alternative theories that explain our observations without requiring a cosmic explosion. And we're going to ask the question that is keeping astrophysicists awake at night. If the Big Bang did not happen, then what did? Let me be clear. I'm not here to sell you on any particular alternative theory. I'm here to show you that the scientific establishment has been far more certain about the Big Bang than the evidence actually supports. They have dismissed critics, ignored anomalies, and added increasingly bizarre patches to keep the theory alive. Dark matter, dark energy, inflation, modifications to gravity. Each one is an admission that something is fundamentally wrong. The first lie is perhaps the most basic. You have been told that the Big Bang is a fact. It is not. The Big Bang is a theory, and theories in science are only as good as their predictions. When predictions fail, theories must change or be abandoned. The Big Bang is failing its predictions at an unprecedented rate. Let us start with what is known as the galactic crisis. In 2022, when the James Webb Space Telescope began sending back its first deep-field images, astronomers expected to see small, primitive galaxies. The early universe, according to Big Bang theory, should have been filled with tiny baby galaxies just beginning to form stars. Instead, JWST found massive, mature spiral galaxies with well-defined structures, some as large as the Milky Way, existing just 300 million years after the supposed Big Bang. This is not a small problem. This is equivalent to finding a full-grown adult in a nursery. One of the astronomers who discovered these galaxies, Rohan Naidu, said he found a galaxy that was inexplicably massive dated back to just 300 million years after the Big Bang, making it older than any galaxy ever seen before. He called his girlfriend over and told her this might be the most distant starlight we have ever seen. What he did not say publicly, but what became clear in the scientific papers that followed, is that these galaxies should not exist. Not if the Big Bang happened the way we have been told. You see, galaxy formation takes time. A lot of time. Stars have to form from gas clouds. Those stars have to live out their lives, explode as supernovae, and scatter heavier elements into space. New generations of stars have to form from that enriched material. Galaxies have to collide and merge. All of this requires hundreds of millions, if not billions of years. But here are these galaxies, massive and mature, appearing almost immediately after the universe supposedly began. The response from Big Bang theorists has been to add more modifications to the theory. Maybe stars formed faster in the early universe. Maybe black holes grew more rapidly than we thought. Maybe there was some unknown mechanism that accelerated galaxy formation. But here is the thing about adding modifications. Each one makes the theory less elegant, less predictive, and more ad hoc. At some point, you're not defending a theory anymore. You're defending your reputation. The second lie builds on the first. You have been told that the cosmic microwave background radiation is proof of the Big Bang. It is not proof. It is evidence that requires interpretation. The CMB is real, we can measure it, but what it actually tells us about the origin of the universe is far less certain than you have been led to believe. The cosmic microwave background is essentially a faint glow of radiation that fills all of space. It was discovered in 1965 by Arno Penzias and Robert Wilson, who were trying to eliminate noise from a radio antenna. This discovery earned them the Nobel Prize, and it became the cornerstone of Big Bang cosmology. The story you've been told is that this radiation is the leftover heat from the Big Bang itself, cooled down over billions of years. But here is what they do not emphasize. The CMB could also be explained by other models. Plasma cosmology, for instance, offers an alternative explanation for the microwave background that does not require a cosmic explosion. In plasma cosmology, electromagnetic forces play a much larger role than gravity in shaping the universe, and the CMB could be the result of energy dissipation in cosmic plasma. The steady-state theory, proposed by Fred Hoyle, also had explanations for the CMB that did not involve a Big Bang. These alternatives were dismissed not because they were disproven, but because the Big Bang had become the preferred narrative. Furthermore, the precision with which the CMB matches Big Bang predictions has been oversold. Yes, the temperature is remarkably uniform across the sky, about 2.7 Kelvin everywhere you look. But this uniformity actually creates what is called the horizon problem, which we will get to in a moment. The point is, the CMB is not the smoking gun proof of the Big Bang that it is made out to be. The third lie is about redshift. You've been told that the redshift of distant galaxies proves the universe is expanding. This is a half-truth at best. Redshift is a real phenomenon. When we look at distant galaxies, their light is shifted toward the red end of the spectrum. The standard interpretation is that this happens because space itself is expanding, stretching the wavelengths of light as it travels. This is called the Doppler shift, and it was the foundation for Edwin Hubble's discovery in 1929 that the universe appears to be expanding. But there is another explanation for redshift that has been around just as long, proposed by the Swiss astronomer Fritz Zwicky in 1929. It is called the tired light hypothesis. Zwicky suggested that light loses energy as it travels vast cosmic distances. The farther light travels, the more energy it loses, and the more it shifts toward red. In this model, redshift is not evidence of expansion. It is simply a property of light traveling through space. The tired light theory was largely ignored for decades, but now, with the James Webb Space Telescope showing us galaxies that should not exist in an expanding universe, some scientists are taking another look. A study published in 2024 by Lior Shamir, an associate professor at Kansas State University, used data from more than 30,000 galaxies to test the tired light hypothesis. His findings suggested that the observed redshift patterns were more consistent with tired light than with cosmic expansion. He specifically noted that the JWST images showed large and mature galaxies in the early universe, which contradicts what we would expect from the standard Big Bang model. Now, before you think this is settled science, it is not. The tired light hypothesis has its own problems. It does not explain everything we observe, but neither does the Big Bang. The point is that redshift, which has been sold to the public as definitive proof of an expanding universe, is actually open to interpretation. Here is where it gets worse. The fourth lie is about the expansion rate itself. You have been told that scientists know how fast the universe is expanding. They do not. In fact, they have two completely different measurements of the expansion rate, and both cannot be correct. This is called the Hubble tension, and in January 2025, it was officially declared a crisis. The expansion rate of the universe is measured by something called the Hubble constant. One way to measure it is by looking at the cosmic microwave background, the ancient light from the early universe. When scientists use this method, they calculate that the universe is expanding at about 67.4 kilometers per second per megaparsec. But when they measure the expansion rate using local observations, things like supernovae and variable stars, they get a completely different number, around 73.2 kilometers per second per megaparsec. That might not sound like a huge difference, but in cosmology, this discrepancy is enormous. Both measurements are incredibly precise, and both should be correct according to our understanding of physics. But they cannot both be correct. Something is fundamentally wrong with either our measurements or our understanding of how the universe works. Adam Rees, a Nobel Prize-winning astronomer at Johns Hopkins University, has been studying this problem for years. In December 2024, his team published the largest study ever using data from both the Hubble Space Telescope and the James Webb Space Telescope. They confirmed that the tension is real. The measurements are not wrong, which means our model of cosmology might be. In January 2025, another team led by Daniel Skolnick at Duke University published results that pushed the Hubble tension even further. They measured the distance to the Coma cluster, one of the closest galaxy clusters to us, using supernovae. Their measurement gave a Hubble constant of 76.5, even higher than previous estimates. Skolnick declared that the Hubble tension is now in our own cosmic backyard, and cosmology is facing a crisis. What does this mean? It means that the universe might not be expanding the way we think it is. It means that our models of dark energy, dark matter, and cosmic evolution might be fundamentally flawed. And it means that the confident predictions you've been hearing about the fate of the universe, heat death in trillions of years, might be completely wrong. The fifth lie is about dark matter. You've been told that dark matter makes up about 85% of the matter in the universe. But here is the truth. No one has ever detected dark matter, not once, not in any experiment, not in any observation. Dark matter is not a discovery. It is a hypothesis invented to explain why galaxies rotate the way they do. In the 1930s, Fritz Zwicky noticed that galaxies and clusters were moving too fast. According to the laws of gravity, they should fly apart, but they did not. So Zwicky proposed that there must be invisible matter providing extra gravity to hold them together. Decades later, Vera Rubin observed that stars in spiral galaxies orbit at the wrong speeds. The outer stars should move slower than the inner stars, like planets in our solar system, but they do not. They move at roughly the same speed, no matter how far from the galactic center they are. The solution was dark matter. Scientists proposed that galaxies are embedded in massive halos of invisible matter that we cannot see, cannot touch, and cannot detect. This dark matter, they say, provides the extra gravity needed to explain the observations. It is a brilliant idea, except for one small problem. We cannot find it. Physicists have been searching for dark matter particles for decades. They have built detectors deep underground, shielded from cosmic rays. They have used the Large Hadron Collider. They have deployed satellites. They have looked for WIMPs, weakly interacting massive particles. They have looked for axions. They have looked for sterile neutrinos. And they have found nothing. Zero. Not a single confirmed detection. Now, the absence of evidence is not necessarily evidence of absence. Maybe dark matter particles are just harder to detect than we thought. Or maybe, just maybe, dark matter does not exist. Maybe our understanding of gravity is wrong. This brings us to an alternative theory called MOND, Modified Newtonian Dynamics, proposed by Mordechai Milgrom in 1983. MOND suggests that gravity behaves differently on very large scales. Instead of inventing invisible matter, MOND modifies the laws of gravity. And in many cases, MOND predictions match observations better than dark matter models. But MOND is not popular in mainstream cosmology. Why? Because accepting MOND would mean admitting that we do not understand gravity, and that would unravel a century of physics. So instead, Scientists cling to dark matter, even though they cannot find it. They keep adding more exotic particles to the list of candidates, each more speculative than the last, and they tell the public that dark matter is real, proven, settled science. It is not. The sixth lie is about dark energy, and it is even worse than dark matter. You have been told that dark energy makes up about 68% of the universe and is causing the expansion of space to accelerate. But here is the truth. Dark energy is not a thing that was discovered. It is a mathematical fudge factor added to equations to make them match observations. In 1998, 2 teams of astronomers were studying distant supernovae. They expected to measure how much the expansion of the universe was slowing down due to gravity. Instead, they found that the expansion was speeding up. This was shocking. Nothing in physics predicted this. So they invented dark energy to explain it. Dark energy is essentially a mysterious force that pushes space apart. It is described as the energy of empty space itself, a property of the vacuum. But no one knows what it actually is. Here is the kicker. The amount of dark energy required to explain observations is spectacularly, absurdly, incomprehensibly wrong, according to quantum field theory. When physicists calculate what the energy of empty space should be based on quantum mechanics, they get a number that is 10 to the power of 120 times larger than what we observe. That is a 1 with 120 zeros after it. This is called the cosmological constant problem, and it is one of the biggest unsolved problems in physics. So dark energy is not some well-understood force, it is a placeholder for our ignorance. It is a label we put on something we do not understand. And yet, cosmologists confidently tell you that the universe is made of 68% dark energy. What they should say is, we observe that the expansion of the universe is accelerating, and we have no idea why. The 7th lie is about inflation. You've been told that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion called inflation. This supposedly solved several problems with the Big Bang theory. But here is the truth. Inflation is not proven. It is a speculative add-on to the Big Bang, invented to fix problems with the original theory. The Big Bang theory, in its simplest form, has 3 major problems: the horizon problem, the flatness problem, and the monopole problem. The horizon problem asks why the universe looks the same in all directions. If the Big Bang happened, different regions of the universe should never have been in contact with each other, yet they have the same temperature. The flatness problem asks why the universe is so geometrically flat. Any tiny deviation from flatness in the early universe should have grown over time, yet the universe remains incredibly flat. The monopole problem asks why we do not see magnetic monopoles, hypothetical particles predicted by grand unified theories. Inflation was invented in 1980 by Alan Guth to solve these problems. He proposed that in the first tiny fraction of a second, the universe expanded faster than the speed of light. This rapid expansion smoothed out any initial irregularities, stretched space to flatness, and diluted any monopoles to undetectable levels. It was an elegant solution. Too elegant, some would say. The problem is that inflation requires a new field, the inflaton field, and a new particle, the inflaton. Neither has been detected. Inflation also requires fine-tuning. The inflaton field had to have exactly the right properties to produce the universe we see, and there are now dozens of different inflation models, each with its own free parameters. When a theory requires that many adjustments and modifications, it stops being a prediction and starts being a story we tell to fit the data. Moreover, a paper published in 2024 in the European Physical Journal questioned whether inflation actually solves the flatness and horizon problems at all. The authors argued that the flatness problem as it is usually posed is not even falsifiable. It assumes the answer it is trying to prove. Similarly, the horizon problem only exists if you assume the universe started in a particular way. If you change the initial conditions, the problems disappear without needing inflation. The 8th lie is about the age of the universe. You have been told the universe is 13.8 billion years old. This number is calculated based on the Big Bang model, but if the model is wrong, the age is wrong, and we have good reasons to think the model is wrong. The age calculation depends on the Hubble constant, the expansion rate of the universe. But as we have already discussed, we have 2 different values for the Hubble constant that cannot both be true. If you use the higher value, the universe is younger. If you use the lower value, it is older. The difference is hundreds of millions of years. That is not a rounding error. That is a fundamental uncertainty and one of the most basic facts about the universe. Furthermore, the James Webb Space Telescope has found objects that appear older than the universe itself according to the standard Big Bang timeline. In March 2024, astronomers announced the discovery of a dead galaxy, JADES GSZ701QU, that stopped forming stars when the universe was only 700 million years old. According to our models, galaxies this old should not exist. For a galaxy to form, grow, and then die requires a timescale that exceeds the age of the universe at that point. This is not an isolated case. The more we look with JWST, the more impossibly old galaxies we find. Either our age estimates are wrong, or the Big Bang timeline is wrong, or both. Yet cosmologists continue to confidently state that the universe is 13.8 billion years old, as if this is settled fact. It is not. The ninth lie is about nucleosynthesis, the process by which elements formed in the early universe. You have been told that the abundances of hydrogen, helium, and lithium match Big Bang predictions perfectly. This is false. The lithium abundance is off by a factor of 3, and this is called the cosmological lithium problem. According to Big Bang nucleosynthesis, in the first few minutes after the Big Bang, nuclear reactions should have produced specific amounts of light elements. Hydrogen, by far the most abundant, helium-4, the second most abundant, deuterium, a heavy isotope of hydrogen, helium-3, another isotope, and lithium-7 in trace amounts. The theory predicts that for every 10 billion hydrogen atoms, there should be about 5 lithium atoms. The problem is, when we measure lithium in old stars, we find only about 1.5 lithium atoms per 10 billion hydrogen atoms. That is 1/3 of what the theory predicts. This discrepancy has been known for decades, and despite countless attempts to explain it, the problem remains unsolved. Some scientists have proposed that lithium gets destroyed inside stars, but detailed models of stellar evolution show this is not enough to account for the missing lithium. Others have suggested errors in the nuclear reaction rates used in the calculations, but even with updated reaction rates, the discrepancy persists. Still others have proposed exotic new physics, like decaying dark matter or changes in fundamental constants. None of these explanations have gained widespread acceptance. In late 2024, a study involving researchers from Italy, France, and the United States examined lithium in the Small Magellanic Cloud, a nearby dwarf galaxy. They found that the lithium abundance in the interstellar medium was 4 times lower than Big Bang predictions. This is significant because the interstellar gas should not deplete lithium. Stars can add lithium, but they cannot remove it from the gas between stars. This result directly contradicts Big Bang nucleosynthesis. The tired light hypothesis, by contrast, predicts lithium production through cosmic ray interactions with carbon and oxygen nuclei, a process that would have been more prevalent in the galaxy's early stages. When researchers calculated the expected lithium abundance using this mechanism, it matched observations far better than the Big Bang model. The 10th lie is about the cosmological constant. You have been told that Einstein introduced the cosmological constant as his biggest blunder, and then it turned out he was right all along. This is a gross oversimplification. The cosmological constant that Einstein introduced is not the same thing as the dark energy that scientists invoke today. Einstein added the cosmological constant to his equations of general relativity to create a static universe. At the time, in 1917, the prevailing belief was that the universe was eternal and unchanging. But Einstein's equations predicted that the universe should either expand or contract. To prevent this, he added a term, the cosmological constant, which represented a repulsive force that exactly balanced gravity. When Hubble discovered that the universe was expanding, Einstein removed the cosmological constant, allegedly calling it his biggest blunder. Decades later, when astronomers discovered that the expansion of the universe was accelerating, they resurrected the cosmological constant to explain it. But the cosmological constant needed to explain acceleration today is completely different from the one Einstein used. Einstein's constant was meant to keep the universe static. The modern constant is meant to make it accelerate. They are not the same thing, and conflating them is misleading. Moreover, The cosmological constant brings with it the catastrophic vacuum energy problem I mentioned earlier. Quantum field theory predicts a vacuum energy density that is 10 to the power of 120 times larger than observed. This is not a small discrepancy. This is theoretical physics failing in the most spectacular way possible. And yet, cosmologists continue to use the cosmological constant as if it is a well-understood quantity. It is not. The 11th lie is about cosmic expansion itself. You have been told that space itself is expanding, carrying galaxies with it. This is often illustrated with the balloon analogy. Imagine dots on the surface of a balloon. As the balloon inflates, the dots move apart. But here is the problem. Galaxies are not like dots on a balloon. Galaxies are held together by gravity, and they do not expand. If space itself were expanding, then everything should expand. Your body, the Earth, the solar system, the Milky Way. But they do not. Why not? The standard answer is that gravity is strong enough on small scales to prevent expansion. Space wants to expand, but gravity holds things together. This sounds reasonable until you start doing the math. If space itself is expanding, then the expansion should exert a force on gravitationally bound objects. This force would be tiny, but it would be there, and over billions of years it should add up. Yet we see no evidence of this. Galaxies do not slowly get pulled apart. Solar systems do not gradually widen. Atoms do not stretch. Some cosmologists argue that the expansion only affects the space between galaxy clusters, not the space within them. But this raises the question, how does space know where to expand and where not to? This is not a trivial problem. It suggests that our understanding of what expansion actually means is incomplete. The 12th lie is about the singularity. You have been told that the Big Bang started from a singularity, an infinitely dense point. This is not true. The singularity is a mathematical artifact, not a physical reality. When the equations of general relativity are extrapolated backward in time, they predict that the universe was once infinitely dense. But infinities in physics are almost always a sign that the theory has broken down. At the incredibly high densities and temperatures of the very early universe, quantum effects become important. General relativity, which describes gravity, does not include quantum mechanics. So when we try to describe the moment of the Big Bang itself, we do not have the right tools. We need a theory of quantum gravity which does not yet exist. Some physicists are working on string theory, others on loop quantum gravity. These approaches suggest that the universe did not begin with a singularity at all. Instead, there might have been a big bounce where a previous contracting universe rebounded into expansion. The point is, the singularity is not a fact. It is a placeholder for our ignorance. And yet, popular science presents it as if it is a proven aspect of the Big Bang. It is not. The 13th lie is about the cosmic microwave background temperature. You have been told that the temperature of the CMB is incredibly uniform, about 2.7 Kelvin in all directions. This uniformity, we are told, is evidence that the universe was once in thermal equilibrium, but this uniformity is actually a problem for the Big Bang, not a solution. If the universe started from a singularity and expanded, different regions of the universe would have been causally disconnected. That means they could never have communicated with each other, not even at the speed of light. So how did they all end up at the same temperature? This is the horizon problem I mentioned earlier. Inflation is supposed to solve this by saying that before inflation, the universe was small enough that everything was in contact. Then inflation blew it up. But as I mentioned, inflation itself is an unproven add-on to the theory. The 14th lie is about the abundance of helium. You have been told that the amount of helium in the universe perfectly matches Big Bang predictions. This is mostly true, but it glosses over important details. The helium abundance is roughly 25% by mass, which does match nucleosynthesis calculations. But these calculations depend on assumptions about the density of baryons, ordinary matter, in the early universe. If those assumptions are wrong, the helium abundance could be explained by other processes, such as stellar nucleosynthesis. Furthermore, helium abundance alone does not distinguish between the Big Bang and alternative cosmologies. Fred Hoyle, the astronomer who coined the term Big Bang in a mocking tone, showed that helium could be produced in stars and in other cosmic processes. The helium abundance is consistent with the Big Bang, but it does not prove the Big Bang. The 15th lie is about the cosmic web. You've been told that the large-scale structure of the universe, the filaments and voids that form the cosmic web, is a natural consequence of the Big Bang and dark matter. But the cosmic web poses a problem for the Big Bang. The structures we observe are too large to have formed in the time available. Galaxies are not randomly distributed in space. They are organized into clusters, superclusters, filaments, and walls, with vast voids in between. The larger structures, like the Hercules Corona Borealis Great Wall, span billions of light years. The problem is these structures take a very long time to form. Gravity has to pull matter together, bit by bit, over hundreds of millions or billions of years. But some of the structures we observe are so large that there should not have been enough time for gravity to assemble them since the Big Bang. This is related to the galactic crisis I mentioned earlier. If galaxies formed too quickly, then so did galaxy clusters and superclusters. The more we observe, the more we find structures that should not exist if the universe is only 13.8 billion years old. Plasma cosmology, by contrast, predicts the cosmic web naturally. In plasma cosmology, electromagnetic forces create filamentary structures on all scales. Plasma naturally organizes into filaments and sheets, driven by magnetic fields. This sponge-like structure is exactly what we observe, and it does not require billions of years to form. The cosmic web, far from being evidence for the Big Bang, might actually be evidence against it. The 16th lie is about the smoothness of the early universe. You have been told that the early universe was incredibly smooth and homogeneous, with only tiny fluctuations that later grew into galaxies. This smoothness is supposedly confirmed by the cosmic microwave background, but the problem is that the CMB is too smooth. The fluctuations we observe are smaller than what Big Bang models initially predicted, and theorists have had to add more and more free parameters to match the data. Moreover, the existence of large structures in the early universe, which JWST is now revealing, contradicts the idea of a smooth beginning. If the early universe was smooth, where did these massive galaxies come from so quickly? The 17th lie is about the isotropy of the universe. You have been told that the universe looks the same in all directions, which is evidence that it expanded uniformly from the Big Bang. But recent observations have found hints of anisotropy, preferred directions in the cosmos. Some studies have found that galaxy spins are not randomly oriented. Instead, there seems to be a preferred axis. This is called the axis of evil, and it should not exist if the Big Bang happened the way we think. Similarly, studies of the cosmic microwave background have found that the larger scale fluctuations, the so-called quadrupole and octopole, are aligned with each other and with the ecliptic plane of the solar system. This is bizarre. The CMB should have nothing to do with the orientation of our solar system, yet the correlation is there. Some scientists have suggested that this is a sign of a foreground effect, something in our galaxy contaminating the signal. Others have suggested that it points to a fundamental asymmetry in the universe. The 18th lie is about primordial black holes. You have been told that black holes formed from the collapse of massive stars. This is true for stellar mass black holes. But there is another idea, that black holes could have formed in the very early universe from density fluctuations. These are called primordial black holes, and they are sometimes proposed as a candidate for dark matter. But here is the thing. No one has ever observed a primordial black hole. They are purely hypothetical. Moreover, the conditions required to form primordial black holes are extremely specific. The early universe would need to have had much larger density fluctuations than we observe in the CMB. So primordial black holes are an ad hoc addition to the theory, invented to solve a problem, dark matter, that might not even require a solution. The 19th lie is about gravitational waves from the Big Bang. You have been told that the Big Bang should have produced gravitational waves, ripples in space-time, that we can detect today. These are called primordial gravitational waves, and they would leave a specific pattern in the cosmic microwave background called B-mode polarization. In 2014, a team using the BICEP 2 telescope announced that they had detected this signal. It made headlines around the world. The Big Bang had been proven, except it had not. Later analysis showed that the signal was actually caused by dust in our galaxy, not primordial gravitational waves. The detection was retracted, and to this day, no one has detected primordial gravitational waves. The fact that we have not detected them is not proof that they do not exist. but it is also not proof that they do. The point is, gravitational waves from the Big Bang are a prediction that has not been confirmed. The 20th lie is about antimatter. You have been told that the Big Bang should have produced equal amounts of matter and antimatter, but the universe is made almost entirely of matter. Where did all the antimatter go? This is called the baryon asymmetry problem, and it is one of the biggest unsolved problems in cosmology. The standard answer is that some unknown process in the early universe caused a slight asymmetry, favouring matter over antimatter. This process, whatever it was, must have violated certain symmetries in physics, specifically CP symmetry. Various mechanisms have been proposed, such as leptogenesis or electroweak baryogenesis, but none of these mechanisms have been confirmed, and the baryon asymmetry remains a mystery. If the Big Bang happened, there should be an explanation for why matter dominates. The fact that we do not have one is a serious problem. Alternative cosmologies, like plasma cosmology, do not require an asymmetry to begin with, because they do not start with a primordial explosion that would have created equal amounts of matter and antimatter. The 21st lie is about neutrinos. You have been told that neutrinos are relics from the Big Bang, and that they fill the universe in vast numbers. This cosmic neutrino background, analogous to the cosmic microwave background, is predicted by Big Bang theory. But here is the problem. No one has ever detected the cosmic neutrino background. Neutrinos are notoriously difficult to detect because they barely interact with matter. The cosmic neutrino background, if it exists, would consist of very low-energy neutrinos that are even harder to detect. So while the CNB is predicted, it is unconfirmed. Now, some scientists will argue that the existence of the CNB is strongly supported by indirect evidence, such as the success of Big Bang nucleosynthesis and observations of large-scale structure. But indirect evidence is not the same as direct detection. The cosmic neutrino background is an assumption built into the Big Bang model, not a proven fact. The 22nd lie is about the density of the universe. You have been told that the universe is almost exactly flat, meaning its density is almost exactly equal to the critical density. This flatness, we are told, is evidence for inflation. But as I mentioned earlier, the flatness problem might not be a problem at all. It is based on the assumption that the universe could have started with any density. If you assume a different starting condition, flatness is not surprising. Moreover, the measurements of the universe's density are not as precise as they are made out to be. Different methods give slightly different results. When you combine visible matter, dark matter, and dark energy, you get something close to the critical density. But each of those components is uncertain. Dark matter is undetected. Dark energy is not understood. So the claim that the universe is flat to within a few percent is built on a shaky foundation. The 23rd lie is about the multiverse. You have been told that some versions of the Big Bang theory, particularly eternal inflation, predict the existence of a multiverse, an infinite number of parallel universes. This is often presented as if it is a logical consequence of the theory. But here is the problem. The multiverse is not a scientific theory. It is untestable. If you cannot make predictions that can be tested, then you are not doing science, you are doing philosophy or metaphysics. Proponents of the multiverse argue that it explains why the constants of nature, like the strength of gravity or the charge of the electron, have the values they do. They say that in a multiverse, every possible value is realized somewhere, and we happen to live in a universe where the values allow for life. This is called the anthropic principle. But the anthropic principle is not a prediction. It is an admission that we do not know why the constants have the values they do. The multiverse is a prime example of how the Big Bang theory has become increasingly speculative and untestable. It is a sign that the theory is in trouble. The 24th lie is about the speed of light. You have been told that the speed of light is constant and has always been constant, but some cosmologists have proposed that the speed of light might have been different in the early universe. Variable speed of light theories, or VSL theories, have been suggested as an alternative to inflation. If light travelled faster in the early universe, it could solve the horizon problem without requiring inflation. VSL theories are highly speculative and are not widely accepted. But the fact that they are even being considered shows that cosmologists are willing to question fundamental assumptions when the standard model does not work. The speed of light, like many other constants, might not be as constant as we think. The 25th lie is about the arrow of time. You have been told that time flows in one direction because of the Big Bang. The universe started in a low entropy state, highly ordered, and entropy has been increasing ever since. This increase in entropy defines the arrow of time, the direction from past to future. But here is the problem. Why did the universe start in a low entropy state? This is a deep mystery in physics. If the Big Bang started from a singularity, a state of infinite density, it should have been a state of extremely high entropy, maximum disorder. But the early universe, as we understand it, was highly ordered. Stars had not formed yet. Galaxies had not formed. Matter was spread out in a nearly uniform gas. This uniformity represents low entropy. How did the universe go from a singularity, which should be maximum entropy, to a low entropy state? This is called the past hypothesis, and it is one of the most profound unanswered questions in cosmology. Some physicists, like Roger Penrose, have proposed that the low entropy beginning requires an explanation beyond the Big Bang. Penrose's conformal cyclic cosmology suggests that the universe goes through repeated cycles, each beginning with a Big Bang-like event. But this is speculative and is not part of the standard Big Bang model. The 26th lie is about the end of the universe. You have been told that because the universe is expanding, it will eventually end in a heat death, a state of maximum entropy where all stars have died, all black holes have evaporated, and nothing interesting can happen anymore. This prediction is based on the assumption that dark energy will continue to accelerate the expansion forever, but as we have discussed, dark energy is not understood. We do not know if it will remain constant, increase, or even reverse. If dark energy changes over time, as some recent studies suggest, then the fate of the universe is completely uncertain. The universe could collapse back on itself in a big crunch, it could rip apart in a big rip, or it could continue expanding forever in a big freeze. The point is, predictions about the end of the universe are based on assumptions that might be wrong. The 27th lie is about the distance ladder. You have been told that astronomers have precisely measured distances to galaxies using a cosmic distance ladder, a series of overlapping methods. But the distance ladder is fraught with uncertainties. Each rung of the ladder depends on the rung below it, and errors accumulate. For example, the distance ladder uses Cepheid variable stars, which brighten and dim in a predictable way. The period of the variation is related to the star's intrinsic brightness. By measuring the period, you can calculate how bright the star actually is. By comparing that to how bright it appears, you can calculate its distance. But this method depends on calibrating Cepheids in our own galaxy, and those calibrations have uncertainties. Similarly, the distance ladder uses type Imige supernovae, which are thought to have a standard brightness. But it turns out that not all type Ia supernovae are exactly the same. There is scatter in their brightness. Corrections have to be applied, and those corrections introduce more uncertainty. The Hubble tension, which I discussed earlier, is partly a result of uncertainties in the distance ladder. Different teams using slightly different methods get different results. This is not a sign of sloppy science. It is a sign that measuring cosmic distances is really, really hard. And it means that many of the distances we have been told are precise are actually uncertain by tens of %. The 28th lie is about galaxy rotation curves. You have been told that the rotation curves of galaxies, which show stars orbiting at the wrong speeds, are definitive proof of dark matter. But there is an alternative explanation that does not require inventing invisible matter. It is called MOND, Modified Newtonian Dynamics, which I mentioned earlier. MOND proposes that on very large scales, gravity behaves differently than Newton predicted. Instead of falling off as 1 over distance squared, gravity falls off more slowly. This slight modification can explain galaxy rotation curves without needing dark matter. It can also explain the observed acceleration of the universe without dark energy. MOND has its own problems. It does not work as well for galaxy clusters, and it does not explain the cosmic microwave background as well as the standard model. But the fact that MOND can explain so much with a simple modification to gravity is remarkable, and it suggests that dark matter might not be the only answer. The 29th lie is about quasars. You have been told that quasars are distant supermassive black holes accreting matter. Their high redshifts indicate that they are billions of light-years away. But some astronomers, notably Holt and Arp, have argued that quasar redshifts are not entirely cosmological. ARP found examples of quasars that appeared to be physically connected to nearby galaxies, yet had vastly different redshifts. If true, this would mean that redshift is not always a reliable indicator of distance. ARP's observations were controversial and were largely dismissed by the mainstream, but they have never been fully explained. If redshift can be affected by factors other than cosmic expansion, then much of our understanding of the universe's structure and history would need to be revised. The 30th lie is about the uniformity of physical laws. You have been told that the laws of physics are the same everywhere in the universe and at all times. This is called the cosmological principle. But there is no guarantee that this is true. Some physicists have suggested that fundamental constants, like the fine structure constant, might vary with time or location. If they do, then our reconstructions of the early universe, which assume constant laws, would be wrong. There have been hints from some observations that the fine structure constant might have been slightly different in the distant past. These hints are controversial and not widely accepted, but they raise the possibility that the universe is more complicated than the Big Bang model assumes. The 31st lie is about the temperature of the early universe. You have been told that the early universe was incredibly hot, with temperatures reaching trillions of degrees. These temperatures are calculated based on running the Big Bang model backward in time. But if the model is wrong, the temperature estimates are wrong. Some alternative cosmologies do not require such extreme temperatures. Moreover, the idea that the universe started infinitely hot at a singularity does not make physical sense. As I mentioned earlier, infinities are a sign that the theory has broken down. The actual temperature history of the early universe, if there was a Big Bang, is much more uncertain than popular accounts suggest. The 32nd lie is about the Planck era. You have been told that the first 10 to the minus 43 seconds after the Big Bang, the Planck time, is the earliest moment we can meaningfully talk about. Before that, quantum gravity effects dominate, and we do not have the physics to describe it. This is true, but here is the problem. The Planck era is not just a boundary of our knowledge. It is a boundary that we might never be able to cross observationally. If we cannot observe or test what happened during the Planck era, then any claims about the origin of the universe are fundamentally speculative. String theory, loop quantum gravity, and other attempts to describe quantum gravity make different predictions about the Planck era. But none of these predictions can be tested. The Planck era might forever remain beyond the reach of science. The 33rd and final lie is the biggest one of all. You have been told that the Big Bang is the best explanation we have for the origin of the universe, and that while there are unanswered questions, the basic framework is solid. This is false. The Big Bang is a theory in crisis. Its predictions are failing at an unprecedented rate. The James Webb Space Telescope is showing us a universe that does not match the model. The Hubble tension is getting worse, not better. Dark matter remains undetected. Dark energy remains unexplained. The lithium problem remains unsolved, and alternative explanations like tired light and plasma cosmology are being taken more seriously than they have been in decades. This does not mean that the Big Bang is definitely wrong. Science is never about absolute certainty. But it does mean that cosmologists should be far more humble about what they claim to know. The public deserves honesty about the state of the field. Instead, they get oversimplified stories that present the Big Bang as if it is proven fact. It is not. It is a model that is increasingly at odds with observations. So where does this leave us? If the Big Bang didn't happen, what did? The honest answer is, we do not know. The universe is far stranger and more complex than any of our models can capture. But that is okay. Science is a process of refinement. We make models, test them, and revise them when they fail. The problem is not that the Big Bang model is being challenged. The problem is that the scientific establishment has been unwilling to seriously consider alternatives. The tired light hypothesis deserves a fair hearing. Plasma cosmology deserves serious investigation. MOND deserves more attention. And the possibility that the universe did not have a beginning, that it is eternal and evolving, should not be dismissed out of hand. These ideas are not fringe. They are legitimate scientific alternatives that have been marginalized because they threaten the dominant narrative. The James Webb Space Telescope is giving us a gift. It is showing us that the universe is not what we thought. Mature galaxies in the early universe, impossibly large structures, discrepancies in the expansion rate. These are not minor anomalies. These are signs that something fundamental is wrong with our model, and we should embrace that. Science thrives on being wrong because being wrong is how we learn. The Big Bang Theory has dominated cosmology for a century. It has been a productive framework that has guided research and led to many discoveries. But its time might be coming to an end. The observations are no longer fitting the predictions. The patches and modifications are piling up. The theory is collapsing under its own weight. And that is okay. That is how science works. What comes next, we do not know. But we can be certain of one thing. The story of the universe is far richer, far stranger, and far more magnificent than any single theory can capture. The 33 lies I have walked you through today are not just about the Big Bang. They are about the nature of science itself. They are about the difference between what we know and what we claim to know. They are about the importance of skepticism, curiosity, and humility in the face of the unknown. The universe does not owe us an easy explanation. It does not owe us a story that fits neatly into a 13.8 billion year timeline. It does not owe us dark matter, dark energy, or inflation. It simply is. And our job, as curious beings in this vast cosmos, is to observe it honestly, to question our assumptions, and to follow the evidence wherever it leads, even if it leads us away from everything we thought we knew. But let us go deeper into what the implications actually are, because this is not just an academic debate. This affects how we understand reality itself. If the Big Bang is wrong, then everything built on top of it, every prediction about the future of the universe, every calculation about its past, every assumption about how matter and energy behave on cosmic scales, all of it comes into question. Consider what it means for our understanding of time. The Big Bang gives us a cosmic clock. It says the universe has an age. It says time itself began at a specific moment. But what if time has no beginning? What if the universe is eternal, constantly evolving but never truly starting? This is not just philosophy, this is physics. An eternal universe would require completely different laws governing its evolution. The thermodynamics would be different. The formation of structure would be different. Everything would be different. Now think about what it means for our search for life in the universe. The Big Bang model says that heavy elements, the elements necessary for life as we know it, were forged in stars over billions of years. The first generation of stars had only hydrogen and helium. It took stellar death and rebirth to create carbon, oxygen, nitrogen, and all the other elements in your body. But if the universe is older, or if it never began, then the timeline for the formation of heavy elements changes. Life could have emerged much earlier than we think, or it could be far more common, or it could be far rarer. The assumptions built into our search for extraterrestrial intelligence, SETI, are based on Big Bang cosmology. If the cosmology is wrong, our search strategy might be wrong too. Think about dark matter for a moment. Truly think about it. Physicists are convinced that 85% of all matter in the universe is something they cannot see, cannot touch, and cannot detect. They have spent decades building ever more sensitive detectors, buried deep underground, hoping to catch a glimpse of a dark matter particle. And they have found nothing. At what point do you admit that maybe, just maybe, the problem is not that dark matter is hard to detect, but that it does not exist? The history of science is full of examples where scientists invented entities to explain observations, only to later discover that a better explanation existed. Phlogiston was invented to explain combustion. Caloric was invented to explain heat. The luminiferous ether was invented to explain how light travels through space. All of these were eventually abandoned. Dark matter might be the phlogiston of the 21st century, a placeholder for something we do not understand. And what about inflation? Alan Guth, who invented inflation, has admitted that we do not know what the inflaton field is, what its properties are, or why it started inflating. We do not know why inflation stopped. We do not know if inflation happened once or is happening eternally, creating an infinite multiverse. Inflation is not a single theory. It is a family of theories with dozens of different models, each with different predictions. When a theory has that many free parameters, it stops being predictive. It becomes a framework that can be adjusted to fit any observation. Some physicists have argued that inflation has become unfalsifiable. If an observation contradicts one inflation model, You just switch to a different inflation model that fits the data. This is not how science is supposed to work. A theory is supposed to make specific, testable predictions. If the predictions fail, the theory is wrong. But inflation has become so flexible that it can accommodate almost anything. And that is a problem. Let us talk about the cosmic microwave background again, because it deserves more scrutiny. The CMB is often called the smoking gun of the Big Bang. But here is what is not often mentioned. The CMB has anomalies, lots of them. The quadrupole and octopole, the largest scale fluctuations in the CMB, are aligned in a way that should not happen if the Big Bang is correct. This alignment is called the axis of evil because it breaks the assumption of isotropy. The universe should look the same in all directions, but these large-scale features have a preferred orientation. There is also the cold spot, a region of the CMB that is significantly colder than the surrounding area. This cold spot is so large and so cold that it is statistically unlikely to have formed by random chance. Some cosmologists have proposed that it is evidence of a collision between our universe and another universe in a multiverse. But this is pure speculation. The cold spot is an anomaly that the Big Bang model struggles to explain. Then there is the issue of foreground contamination. The CMB signal has to be extracted from a noisy sky. Our galaxy emits radiation. Dust emits radiation. All of this has to be subtracted out to see the CMB. The subtraction process involves assumptions and models. If those assumptions are wrong, the CMB map we see could be wrong. In fact, different teams analysing the same data have produced slightly different CMB maps, which suggests that the process is not as clean as we would like. And let us not forget the hemispherical asymmetry. The CMB is slightly brighter in one half of the sky than the other. This should not happen if the Big Bang is correct. The early universe should have been uniform, but it was not. The hemispherical asymmetry is another anomaly that challenges the standard model. What about gravitational lensing? You have been told that gravitational lensing, the bending of light by massive objects, confirms general relativity and supports the existence of dark matter. But gravitational lensing also supports MOND, the modified gravity theory I mentioned. In fact, some lensing observations are better explained by MOND than by dark matter. The point is, gravitational lensing is evidence for something, but it is not definitive proof of dark matter. There is also the bullet cluster, often cited as the best evidence for dark matter. The bullet cluster is the result of two galaxy clusters colliding. When they collided, the hot gas in each cluster slowed down due to friction, but the galaxies themselves passed through each other relatively unscathed. Gravitational lensing shows that most of the mass is not where the gas is, but where the galaxies are. This is interpreted as evidence that dark matter exists, and that it does not interact with normal matter. But alternative explanations exist. Some MOND theorists have proposed modifications that can explain the bullet cluster without dark matter. The evidence is not as clear-cut as it is often presented. Now let us address the elephant in the room. Why is the scientific establishment so resistant to alternatives to the Big Bang? Part of it is simple human psychology. Scientists have invested their careers in the Big Bang model. They have built their reputations on it. Admitting that the model might be fundamentally wrong is hard. It means that decades of work might have been based on incorrect assumptions. It means that textbooks need to be rewritten. It means that funding priorities need to shift. It is easier to add another patch to the theory, another free parameter, another exotic particle, than to start over from scratch. There is also the issue of groupthink. Science is supposed to be about questioning assumptions and following the evidence, but in practice, science is a social enterprise. Scientists work in institutions, they apply for grants, they publish in journals, and all of these processes are influenced by consensus. If the consensus says the Big Bang is correct, then challenging the Big Bang is risky. You might not get funding, you might not get published, you might be labelled a crank. This stifles dissent and discourages original thinking. Halton Arp, the astronomer who questioned quasar redshifts, was denied telescope time because his proposals challenged the mainstream view. Fred Hoyle, who coined the term Big Bang, was never awarded the Nobel Prize for his work on stellar nuclear synthesis, arguably because he remained a critic of the Big Bang. These are cautionary tales. Science is supposed to be self-correcting, but that only works if scientists are free to challenge prevailing theories without fear of professional repercussions. And then there is the issue of funding. Most cosmology research is funded by government agencies and universities, which tend to support mainstream research. Alternative theories are often seen as too risky to fund. Why invest in plasma cosmology or tired light when the Big Bang is the accepted model? This creates a self-reinforcing cycle. The Big Bang gets more funding, which leads to more research, which leads to more support for the Big Bang. Alternative theories are starved of resources and remain underdeveloped. But the James Webb Space Telescope is changing the game. JWST is not biased toward any particular theory. It just observes the universe as it is, and what it is showing us is forcing cosmologists to confront uncomfortable truths. The galaxies in the early universe are not what we expected. The expansion rate of the universe does not match predictions. The structures we see are too large and too mature. The universe is not cooperating with the Big Bang model. Some cosmologists are starting to acknowledge the crisis publicly. In January 2025, Daniel Skolnick declared that the Hubble tension is now a crisis. In September 2024, Lior Shamir published a study supporting tired light. In March 2024, astronomers announced the discovery of dead galaxies that should not exist. These are not fringe scientists. These are researchers at major universities, publishing in peer-reviewed journals. The cracks in the Big Bang are widening, so what should we make of all this? Should we abandon the Big Bang entirely? Not necessarily. Science is a process of refinement. The Big Bang model might be salvageable with major modifications, or it might need to be replaced entirely. The key is to remain open to possibilities and to follow the evidence wherever it leads. One thing is certain. The universe is far more mysterious than we have been led to believe. The confident pronouncements about the age of the universe, the fate of the cosmos, the nature of dark matter and dark energy, all of these are built on assumptions that are increasingly shaky. We need more humility in cosmology. We need more willingness to question. We need more support for alternative ideas. The Big Bang has been a useful theory. It has guided research for a century. But it is not sacred. It is not beyond question. And the observations from the James Webb Space Telescope are screaming at us to pay attention. The universe is telling us something. It is telling us that our models are incomplete. It is telling us that we need to think bigger, think differently, think more creatively. The 33 lies I have shared with you today are not just about cosmology. They are about how science is communicated to the public. They are about the gap between what scientists actually know and what they claim to know. They are about the importance of skepticism, not as cynicism, but as a tool for discovery. Every great breakthrough in science has come from someone questioning the accepted wisdom. Copernicus questioned geocentrism. Galileo questioned Aristotelian physics. Einstein questioned Newtonian mechanics. And today, a new generation of cosmologists is beginning to question the Big Bang. The universe does not care about our theories. It does not care about our reputations or our careers. It simply exists, vast and indifferent, waiting for us to understand it. And understanding requires honesty. It requires admitting when we are wrong. It requires being willing to start over when the evidence demands it. So here is my challenge to you. Do not take anyone's word for it, not mine, not anyone else's. Look at the data yourself. Read the papers, examine the assumptions, ask questions, demand evidence. Science is not a set of dogmas handed down from authorities. Science is a method, a way of interrogating nature. And the most important part of that method is doubt. The Big Bang might be right, or it might be wrong. But either way, the journey to find out is worth taking, because that journey is what science is all about. Not the destination, but the process. Not the answers, but the questions. Not the certainty, but the wonder. Thank you for staying with me through this deep dive into the problems with the Big Bang theory. The universe is waiting to reveal its secrets, and the only way we will find them is by being brave enough to look beyond what we think we already know.